Okay, welcome to section 8.3, rational functions and their graphs. And judging by the title, you can see that we've been exploring rational functions, and now we're going to be looking at the graphs that they produce. Okay, these are non-polynomial functions, and so what we're going to do is study the various types of graphs that we can get with rational functions. Okay, the big point here is that if a rational function has a polynomial in the denominator, the polynomial can have a gap at each zero, a hole at a point, or an asymptote. So those are the big three things that can happen. You can have a gap, you can have a hole, okay, or you can have the asymptote. And below are just three types of functions we can have. And this one we're going to study is continuous and discontinuous functions. So the first one's continuous. I can draw that function without lifting my pen. Now this is what we're talking about, a hole or a gap. Okay, there's a hole in the graph, so the graph is defined everywhere, but at a particular point. We still say this is discontinuous because the graph has that hole, or puncture they call it. And finally, the last graph, this is another discontinuous function, and this is a rational function that has asymptotes. It has two of them, a vertical asymptote at A and a horizontal asymptote, let's say, at B. Okay, so these are the functions that we're going to look at. Primarily, we're going to be seeing this type of function and this type of function today. Alright, so when we talk about punctures or holes in the graph, we have to look at this idea of what discontinuity means. Something that's not continuous. You can't draw the whole graph without moving your pen or lifting your pencil up. So there's really two types that we're going to look at. We're going to look at something that's removable, and that's when you have that little puncture hole, and non-removable discontinuity, and that's when we have an asymptote. So if a real number, if A is a real number that makes the denominator 0, and A is in the domain of f of x, we say that we have a point of discontinuity. Okay, so if we have an A that makes the denominator 0. Okay, now in part 1 here, removable discontinuity, we see that if A is -2, we make the denominator 0. But notice we have the same factor in the numerator. Those can cancel out. Okay, so that's what we mean by removable. We can actually remove the 0. Okay, so this is removable discontinuity at x equals -2. So that means there's going to be a hole at -2, 1. Because if we plug -2 into what remains, x plus 2 and x plus 2 become 1, you're left with just x plus 3. So if we plug -2 in there, we get 1. So the hole would be at -2, 1. So that's what it means to be removable. We see the 0, okay, but it can be removed. Now when you look at this function, -2 is not in the domain. You have to make sure you're aware of that. So this simplified function has to have the same domain as the blue function here. They have to have the same domain. X can't be -2, and there's going to be a hole there. It's going to be undefined there. Okay? Non-removable, and this is a lot of what we're going to see when we graph rational functions. We have a vertical asymptote, in this case at x equals 2. So when we look at this equation, x minus 4 over x minus 2, they're both prime, meaning there's nothing common between both of them. We can't cancel out 2 and 4 because of the operation here. So this is a simplified polynomial, simplified rational expression. Okay, and since we can't simplify it, 2 would give us a vertical asymptote. Okay, our first example, it says what is the domain and the points of discontinuity, if they exist, of f of x equals x plus 3 over x squared minus 4x plus 3. Now, anytime we're looking to find points of discontinuity or even trying to graph functions, number one thing you always want to try to do is factor, if possible. So I look at the numerator, I can't factor that. All of a sudden, I look in the denominator and I have this quadratic polynomial. So I got to think, can I factor this? Turns out I can, and two numbers that multiply to be 3 and add to be -4 are -3 and -1. But then I look. There's nothing I can simplify. There's nothing I can remove. So there is going to be discontinuity here because we can make the denominator 0. But there's nothing that's going to be removable because I cannot simplify anything here. So we can't simplify the polynomial any further than this. We do have non-removable discontinuity. Okay? And in this case we have vertical asymptotes. at 3 and 1. Okay, so now they're asking what's the domain of the function. The domain is from negative infinity to 1, union with 1 to 3, union with 3 to infinity. Okay, so there's 3 parts. We can go all the way to 1, and we can't use 1. From negative infinity to 1, we're good. Then we can use all the values between 1 and 3, our 2 vertical asymptotes, and then everything after 3 also works. Okay, and when you start to graph these, you'll be able to start to visualize and see these asymptotes and these domains much better. So example 2 and example 3 are along the lines of example 1. We're going to find the points of discontinuity, okay, and we're looking at f of x is equal to x minus 5 over x squared plus 1. So number 1, try to factor. Can't factor the numerator, can't factor the denominator. A lot of kids would say, oh, x plus 1 times x plus 1. This is not the difference of 2 squares pattern. It's the sum of 2 squares, but we don't have a factoring pattern for that. So you can't factor either the numerator or the denominator. There's no x value that makes the denominator 0. I cannot plug something into x and make that negative so we can cancel out the 1. Some people will say 0. Some people would say negative 1. But remember, anytime you square a negative number, you get a positive result. So there's nothing here that would make the denominator 0. So there are no points of discontinuity. Okay, this graph, this function, in this case, would be continuous. Okay, so we know there's no x value that makes the denominator 0, so the domain is all real numbers. There's no restrictions on x because we can't make the denominator equal to 0. So no discontinuities there. All right, example 3. Again, find the points of discontinuity of this function. Now I'm going to try to factor this function, and I look at the numerator and I see it's a quadratic, so I can factor 2 numbers that multiply to be negative 4 and add to be negative 3 are negative 4 and plus 1. But notice how in the numerator I have a factor of x minus 4 and the denominator is x minus 4. I have something I can remove. Now, if x is 4, the denominator is 0, so I still need to think about that. So I cancel out or simplify this rational expression, and x minus 4, those factors become 1, and I'm left with just x plus 1. So the simplified rational expression is x plus 1 after the simplification. If I plug in 4, I get 5 into that function, so there's going to be a hole at 4, 5. Okay? So this is removable discontinuity. This is where you'd see a linear graph with a hole or a puncture at 4, 5. Again, 4 is not in this domain. 4 makes this rational expression 0. The simplified form must have the same domain as this above rational expression, or else we wouldn't have similar, the simplified form wouldn't be true. You have to have the same domain. Okay? The domain here is from negative infinity to 4 in union with 4 to infinity. There's only one number that doesn't work, and that would be 4. This is not a final here is not a lasted problem, but we're going to get into the second video, and it's going to talk about graphing, but we're going to talk about vertical asymptotes on this slide. Vertical asymptotes occur when each real zero of the denominator. So in the last example, 4 gave us a 0 in the denominator. So that would give us a vertical asymptote, and you have to make sure there's nothing common in the polynomial. So we always look and say, what makes the denominator 0? If we have a number that works for x, that's a vertical asymptote. The only time that doesn't happen is if we have something common in the numerator and the denominator that we can remove. Okay? So the numerator and the denominator have, if the numerator and denominator have this in common, and m is less than n, x minus a is still a vertical asymptote. Okay, and we'll see that. So let's say if we had x squared over x, or excuse me, x over x squared, we would still have x equaling to 0 being a vertical asymptote. So if the power is less in the numerator than the denominator, a vertical asymptote will still occur. Okay. That's it for the first video. In the second video, we're going to talk about horizontal asymptotes and actually graphing what these rational functions would look like. Okay, so we'll see you for video 2.